In this video, we're going to talk about the derivative as a function. Okay. So in the last video, we talked a little bit about the average rate of change and the instantaneous rate of change, and how the different forms of the function for those. And so here, when we talk about the derivative, as we mentioned in that previous video, we are looking at the limit of the average rate in order to get the derivative. And so here, as a function, we're just going to denote this f prime of a, where f of x is our function and a is the point that we're taking the derivative at. Okay? And the alternate form, again, just like in the last video, is given by f prime of a equal to the limit as x goes to a of f of x minus f of a over x minus a. So again, in both cases, we're still looking at the limit of an average rate. Here, this form is what we call our definition of the derivative. And this is what you're going to want to know, because in some cases you are going to be asked to find the derivative using the definition. And so we'll look at an example of that here in just a second. And then some cases you're going to be asked for the alternate form. And again, you'll get the same answers, either way you do it, but it just depends on the method you're using. Okay? So in our first example, let's look at f prime of x. We want to find that for f of x equaling 4x cubed plus 2. Okay? So this is another polynomial type function. It's going to work very similar to what we did last time. So here we want to use the definition to find this. So our definition again says that f prime of x is going to equal the limit as h goes to 0 of our f of x plus h minus f of x over h. And again, the first thing we're going to want to do to simplify this, or to solve for the derivative, is to evaluate the function at the two values. Okay, so we'll have the limit as h goes to 0. F of x plus h means, again, 4x plus h cubed plus 2. That expression minus our f of x, which is 4x cubed plus 2. All of that divided by h. From there, we're going to go ahead and expand. Okay. This one I'm actually going to write out because I know not everybody is familiar with cubing. So let's write this one out. We'll go ahead and FOIL. So getting our expression here, we'll get 4x cubed plus 3x squared h plus 3xh squared plus an h cubed plus 2 minus a 4x cubed minus 2. Okay. And so notice there we went ahead and distributed that minus sign in the second term there. Okay. From there we can combine terms. So we can see the 4x cubed is going to cancel there. Also those 2's will cancel out. And so what we're left with is a 12x squared h plus 12xh squared plus a 4h cubed. Again, just like with our velocity problem and the examples we've done before, at this point, once I've simplified down, I should be able to cancel an h out. If, when you're doing the definition, you ever reach a point in the calculation of the derivative where you get here and you cannot cancel your h's out, you've done something wrong. You need to go back and look at your calculations and make sure you did things algebraically correct. Okay? Oftentimes students will find like they have a plus 4 out here or a plus 5 or something else, and that just means you didn't cancel correctly or you forgot to distribute your minus signs. Okay? At this stage you should always be able to cancel, at least for any function that we would do or look at. Okay, so here we can cancel out an h. We'll get a 12x squared plus a 12xh plus a 4h squared. Taking our limit says we'll get a 12x squared plus 0 and 0. So 12x squared is our derivative. So this is our f prime of x. Okay. Once we get the derivative, again, this is a function, so we can treat it just like a function. So one of the things you may be asked to do is taking this derivative and say, find f prime at negative 2. Okay, and so once I have my f prime of x, then I can do that. I can take and just put in negative 2 so that we see f prime of negative 2 is going to equal 12 times the negative 2 squared, which we can simplify as 4, so this would be 48. So now let's look at an example with the alternate form. So here we want to use the alternate form to find f prime of negative 3 for the function f of x equals 4 over 1, the square root of 1 minus x. Okay? So our alternate form says that f prime of a is going to equal the limit as x approaches a of f of x minus f of a over x minus a. Okay, so we're still looking at a limit of an average rate, it's just a slightly different form. Okay, so in this case, because we're looking for f prime of negative 3, that's going to be our a. So the limit as x approaches negative 3, f of x is exactly what it looks like, so 4 over the square root of 1 minus x, minus f of a, which if we plug in is 4 over the square root of 1 minus a negative 3, all over x minus a negative 3. Okay? So before we actually algebraically manipulate this, we're going to start by simplifying some of these expressions. So the limit as x goes to negative 3, we can see here, if we look, we'll get 1 plus 3, which is 4, square root of that is 2. So we're looking at 4 over the square root of 1 minus x minus 2 all over x plus 3. Okay? So now it's a matter of simplifying. Well, here we can see we've got a fraction and a number, so we're probably going to want to get rid of that fraction. So we'll get a common denominator and invert and multiply. But to get rid of that root, okay, because that negative 3 is still a problem there, so here we want to rationalize. So we're going to multiply top and bottom by the conjugate. And I do actually mean rationalize the numerator because we want to try and find something in the top to cancel with that factor in the bottom. And so we're going to have to rewrite the top, which means using our conjugate, top and bottom, and we'll multiply that out. Okay, so here when we multiply out, we'll get a 16. We'll get minus an 8 times the root plus an 8 times the root, so those will cancel out. Minus 4 times the 1 minus x over square root 1 minus x, x plus 3. Okay. So here it doesn't look like anything cancels, but if we rewrite this, so we can see we'll get a 16 minus 4 plus a 4x over the square root of 1 minus x times x plus 3. And so here we can see when we factor out the 4, those x plus 3's will cancel out. And so we get the limit as x goes to negative 3 of 4 over the square root of 1 minus x, which in this case, when we evaluate, again, plug in negative 3, we'll get 4 over 2, or our limit is 2. And so f prime at negative 3 is just going to equal 2. Okay. Now this function was kind of interesting, because if you notice, our f of x and our f prime of x are very similar. Okay. That is not always going to be the case. But in some cases you will find that you get functions that are very close to what their original function looks like. And part of that reason is because, again, it is a function and it should relate to the derivative. Okay? So here let's, for example, take a graph of f of x. And we want to sketch the graph of f prime. Now, if you remember how we defined our function, it is slopes of tangent lines. Okay? So here, when we're talking about taking this graph and graphing the derivative, we're basically looking at the slope of this and trying to figure out what the graph of the slope looks like. And so here at different points, we can see some things. So I didn't label this graph purposely, and that's because I don't want you to get bogged down with the numbers, but just the general idea of what the slopes are doing. Okay? So at some particular points, in particular here, we can see we've got a horizontal slope at kind of all the highs and low points on this graph. Okay? In between those, we can see some things as well. So, for example, in between these two, we can see that we've got some kind of a positive slope. And in between here, we've got something kind of negative. Okay? On the other side here, again, it's going positive, and over here, it's doing something negative. I drew that one way off the line. Let's try that again. Okay? And so if we think in general about what the slope is doing, it's starting negative, okay? And notice I didn't say decreasing. I do mean it's negative, so it's going to be below the x-axis before we start, when we start the graph of the slope. So it's negative, then it reaches 0 at some point, then it turns positive, reaches 0 again, and then decreases, or sorry, is negative, 0, and positive. Okay? And so if we put that together with kind of what we're looking at here, so again, it's going to start negative, goes up to 0, 0 meaning intersects the x-axis, it becomes positive, it's slowly going to change the positivity of the slope. So it may be really positive and then it comes back down, but it's still positive, reaches 0 again, then it becomes negative for a while, changes direction, so it could be really negative and then slowly tapering off. It's going to hit 0 again, and then from there it stays positive. So the graph of our slope we can kind of figure out in terms based on the original function. Okay? And again, you've got to be a little careful. If I have numbers on the graph, you can make your slope graph a lot more accurate. But just looking at what the function is doing, I can get a general idea of what the slope is doing. In other words, I know I can get a general idea of what f prime of x is doing. So there's just a couple other things we want to look at when talking about the derivative as a function. And the first is your different notations that you're going to see. Okay? We've already expressed the f prime notation to talk about the derivative. But in some cases you may not have a function but more of an equation. So if you're looking at maybe a y in terms of x, we can call y prime the derivative, or we can use the what we call the Leibniz notation. To get the derivative, which is the dy dx. Or again, if I'm looking at a function f of x, I can use df dx. And again, both of these, the Leibniz notations, just say I'm taking the derivative of f or y with respect to the variable x. So in this case, x is the domain variable. Okay? This notation is often used if you're given an expression, not necessarily written as a function. So maybe I don't have an f of x equals, but I've just got an expression that I want to take the derivative of. Then we can say it's the derivative of the expression with respect to x. And again, this notion of with respect to is useful because not only do we talk about derivatives for two variable functions, we also talk about derivatives for higher variable functions. And for all the engineers and scientists, those students will end up taking Calculus 3, and this notation will be used a lot more. Okay. The other notation that you'll see is this differential operator, d. This one is not used as widely as your Leibniz and your function notations, but again, same thing. This is saying basically we're taking the differential operator of f of x, or differential of x, of f with respect to x. So both kind of say the same thing. Again, you're probably going to see this notation here and your f prime or y prime notation most often. Okay. Some other properties that you're going to notice with your derivatives, or maybe you're not going to notice, but they're going to be useful for some of the things you're going to do later. And that first one is, if f prime exists, then f is said to be differentiable at a. And this notion of differentiability just means if I'm looking at the function at a particular point, can I find the derivative of it? Okay. If f is differentiable at a, and every point within an interval, then it's differentiable on the interval. So now, like continuity that we talked about a little while ago, we said a point was continuous at a single value if we could make three conditions hold. Okay, and then we expanded that to say it's continuous over an interval if it's continuous at every single point within the interval. And so the same thing is true with differentiation. I can do it at a single point, or I can find the derivative over an interval. This last property says that if f is differentiable at a point, then it is continuous at that point. And here, what that's saying is, if I'm able to find this instantaneous rate of change at a particular point, the limit does have to exist. Okay? Because I've got to be able to come in from both sides and have the limit from one side equal the limit from the other in order for the derivative to exist. Okay? One thing to note is that the reverse of this is not true. If f is continuous, this does not imply that f is differentiable. And the best way to describe this, or to give an example of this, is to look at the graph of a particular function. And so here, if I've got a graph that does something like this, okay? And so here at this point A, first off we can see that this is continuous. F of A is defined. The limit from both sides are equivalent. They're both going to whatever this value here is. We'll call it L. And if we look at the function value, it's equivalent to the limit. So here the function is continuous. But the reason it's not differentiable is because if I look at the derivative of that, remember the derivative is synonymous with slope. So if I'm looking at the slope at that point, the slope of the curve there is basically a vertical line. And if you remember, way back in pre-calc when you talked about linear equations, the slope of a vertical line is undefined, which means here our derivative is undefined. So I can have something continuous where the derivative doesn't exist. And so that's why the reverse of this statement is not true. If it's differentiable, it is definitely going to be continuous. But if it's continuous, that does not imply differentiability.